So I get to have the pleasure of teaching you about lists, both the data structure, linked lists, as well as the ADT that kind of wraps around them, and I'm forcing you to talk about and use and learn the C++ default implementation in your lab. But we're going to learn how to make them from scratch. I'm so excited. It's very fun. And then also, very important slide, your textbook for pretty much the rest of this class has pseudocode in it. We've been reading the textbook, I hope, because you get credit for doing that. But like the pseudocode of your book is pretty much, which looks very similar to C++, easily translatable, right? Pretty much has everything we're talking about. Like if you want to go and not stare at my diagrams, it's very good practice. There is actual code in your book for all the things we're talking about today, and then also in the future. Okay, so just keep that in mind. It is very useful to be reading that textbook. And with that, let us talk now about linked lists. It is the data structure linked list is a way of arranging memory. We're going to talk exactly about like what memory looks like, what boxes are where. And there's also a list ADT though, where you can interact essentially with a linked list. So let's motivate. Why in the world would I want this thing called a linked list, which I have explained once upon a time? It's like a competitor to arrays and vectors. Like a linked list is a way to store data in an order. So like, what's so bad about what we have so far? Like, why don't we just stop at this? What are the pros and cons of having an array or a vector? All right, let's figure this out. So there are some very good things about having arrays. Like we love them. That's why we learn about them. Arrays and vectors, they're contiguous in memory. We know that, right? You know that if this is address 100 where this thing starts, if it's an array of ints, this next thing is at address 104. I know exactly where these things are. The next one is at address 108. They go in order, they're contiguous. It's very easy to move around because of that, because you can calculate an address with just some math and go exactly there. I can easily get to the third thing by going to that, which is also an index, right? Go to index 2 or go to that address. Essentially, going to an index is computing an address secretly and going there. It's doing pointer arithmetic. So that's all the stuff that we have. And those are great things about arrays and vectors. They all share those qualities, right? There are plenty of cons, though, when you try to do some stuff. There's things that we've bumped into, I'm sure, as we've tried to use arrays and vectors. One very, very glaring thing is that with arrays especially, you are stuck with the size you've said. This is a size 7 array. It's not getting any bigger. Not getting any smaller either. So that's a problem. With vectors, you can push back, but you know the secret now. It's like, you got to copy things over, potentially resize, and that gets a little complicated and unwieldy. So there's that. And then also, this is another thing that's very important to discover, even if we haven't run into it yet. It's really hard to put stuff in the middle or even at the start of an array. If you've got stuff there already, let's say I want to add the number 0 right there and preserve everything else. Well, you better hope that you have room, first of all, if it's an array, and then you got to shuffle everybody over, right? It's a linear time algorithm to do that, isn't it? If you had room. And then now you can shove the 0 there and it's fine. But like that's a lot of work. If you had a million sized array with some room at the end, you got to shuffle all those million elements over, so 999,000 whatever over, and then you can add the thing at the start. That's disgusting, yes? That's a linear time thing. That shouldn't be that hard, but it is for arrays. Enter linked lists. All right, they're a competitor to arrays and vectors, and this is a drawing of the memory, essentially, what memory looks like for a list that holds the numbers 1, then 2, then 3 in that order. All right, so I use that kind of syntax to quickly talk about a list. This is Python syntax for lists, but this is what it looks like. It's just pointers all day long. I'm so sorry if you hate pointers. You're gonna love them by the end of this class, one way or another. So a linked list is holding 1, then 2, then 3 in a chain of pointers and a chain of nodes. All right, so a linked list is made up of a bunch of things called nodes. These are our nodes. They're little boxes with some boxes inside. And each node has 2 pieces inside of it. There's always 2 pieces for a node. A node is one element of a linked list, and it holds a piece of data. So here's the data part, like it's got the 1, that's the thing, that's the first element of the list. And then it also holds something that's called next. That I'll call it next. And it's a pointer. That next thing is a pointer to the next element of the linked list. It's a pointer to another node. Where do I go next? Where could I go next? Okay, that's what a linked list is all about. Yeah, and that's kind of how it works. There's a pointer to the first node. That's how you keep track of where your list starts. And then the next pointer takes you to the next node. Like that's how you know that 2's there. You can do this in a loop. Once you're at the 2 node, you can find its next pointer to get to the 3 node. And then you can get the 3 out. And then you notice there's a way to mark that the list is empty, or not empty. There's a way to mark that the list is done, that there's nothing left. It's you put a pointer that you cannot ever go to there. That's what you do. You put the null pointer right there, which is the 0 address. So 0 or capital null in C land or nullptr in C++ land, that is the null pointer. That's an address. It's the 0 address. You can never go there. That is a perfect thing that marks a pointer that's useless, something that could be the end of our list. All right, so it marks that there's nothing left. Don't even try. All right, it marks the end of a list. That's kind of nice. We got one of those. So yeah, that's pretty much what linked lists look like. When you make a node, you're going to make it on the heap because you want to kind of pass around this list to people. So new nodes are almost always made on the heap, unless you have a really good reason to do otherwise. On the heap. Boop. Something like that. And so like you make a brand new node, shiny new on the heap. It has a data part and a next part. You can put stuff in the data part, and you can put another pointer in the next part. All right. Any questions so far? You kind of see it? That's what they look like. It's a bunch of nodes. You can have a pointer to the last node to immediately get there if you want to put something at the end. Here's the beauty of a linked list. Here's at least one thing that it solves. It's flipping around this pro and con list. There's some things that are hard that are easy with arrays. There's some things that are easy that were hard with arrays. That's why it's a competitor. So one thing that's really nice is it solves this problem. Hard to add stuff to like the start or something. It is super easy to add something to the start of a linked list. Super easy. Even if it was 1,000,000 elements long, all you got to do is make a new node. Say I want to add 0 to the start of this list. Make a new node on the heap. Put 0 in the data section. Put in the next section the thing that I want to be next, which is the old first. And then say, hey, first, you're now this node. No matter what size that list was, all I had to do was make a thing on the heap, set some values, constant time. Yeah, constant time, not linear time. That's lovely. And that is one of the nice things and the reason we want to learn about it. Does that make enough sense? Questions about that? Before we go to code? We ready for the code? All right. So yeah, let's learn how to make this list. Let's make the list 1, then 2 in code. All right. And so here is what every node looks like. This is the struct definition for nodes. Every node has a piece of data and it has a next pointer, and this is how I draw them, even though I've drawn structs in a different way before. Like if you make a node n, usually like I've drawn structs like this, but it's just too complicated, too much time to do it this way. Like there's a data piece inside of it, and then there's a next piece inside of that. Like this, the null pointer is, let's say next is null, it's the end of the list. And then the data is 42. I will be drawing that for linked lists like this. 42 for the data, and then I'll do a little slash to mean it's the end if it's a null pointer. So that's just shorthand. It means that. It's really just a struct where you got pieces you can go to. All right. So that's what it looks like. And yeah, it's very odd to be like, I'm defining the struct node. This is the new type, and I'm using it inside of myself. That's recursive. That's kind of cool. So we don't run into trouble with infinities because of the star. The address stuff kind of cuts that off, which is nice. But yeah, it is a recursive type, we could say. It's got itself within itself, which is fun to think about. So let me create this list in code for you. It'll be the list 1, then 2. And this is the correct lecture number, yeah? Cool. So I'll make a file called 12.cpp. So we have nodes. We need to make a bunch of nodes. Struct node. It's got some data. Let's make it a linked list of ints. So it's integer data. It could be double data. It could be string data, whatever you want. That's fine. And then it's always something called next, a pointer to yourself. Not a pointer to something of your same type, though. A pointer to some other node that is the thing that comes after you, or null if nothing comes after you. All right, so that's the struct definition. And now I can make some nodes. I'll make the 1 node and the 2 node just on the heap is where you want to make them. So so node star 1 equals a new node, please. Make me a new node on the heap called 1. Make me another node on the heap called 2. And now essentially I've made this diagram, right? I've got 1 pointing to a node and 2 pointing to a node, 2 separate nodes on the heap. Now I got to link them together and do all this. All right. So let us build this further. So all right, 1 should have 1 as its data. 2 should have 2 as its data. So let's do that. 1's data is the number 1. 2's data is the number 2. Cool. We got the data parts filled in. And now we got to do the nexts. 1's next, this thing, should be a pointer to the 2 node, right? Should be the address of the 2 node. So 1's next equals 2, because 2 lives on the heap. It is already a pointer to that thing. Okay, so just say 2 by itself. It is a pointer. And then we got to say that 2 has no next thing. 2's next, it's not circular. It doesn't become itself. We mark it as the end of the list with a null pointer, the 0 address. So the last element of the list is marked with the null pointer. So we've got essentially this so far. Are you following me? Is it making sense? All right. So I got those. And now we can bring in first and last usually. That's when you have a full list, you really care about keeping track of the first thing and the last thing, so you can add stuff to the beginning and the end easily. And so let's make those pointers. So first is just the same as 1, right? First is holding that address. So the first thing is the 1 node. So node star first is the 1 node, the address of the 1 node, and then the last node on the list is the 2 node. Cool. And that is the code. I haven't told you how to like go through it yet, but like it would be like 1's data printed out. But that creates this memory. Are there any questions about that? Does it make sense? Can you see it? So yeah, please yell at me if you have any questions about that. It is also important to remember like what's on the stack, what's on the heap right now, because everything, we've made these nodes on the heap, but everything else with names and stuff, they live on the stack, all right? It's like what's where is a good thing to go to right now. It's like stack stuff, heap stuff. A good rule of thumb is like you said new, that's the only stuff that's going on the heap, all right? So there is a big difference. Let's see, we've got 1 and 2 are names. Those are local variables. 1 and 2 are local variables. They hold node stars. So 1 and 2 are local variables. They live on the stack. In main stack frame specifically. And they're pointing, though, to nodes on the heap. So new node, new node. We made 2 nodes on the heap, and one pointed to one of them. 2 pointed to the other one. That's what's going on, just like that. That's those 2 lines doing that. And then we started saying 1's data is 1, 2's data is 2. So it's like boop, boop. That's what we did. Going through stack stuff to get to heap stuff. 1's next is 2, 2's next is null. 1's next is 2, 2's next is null. And then we created first and last as just names, aliases of 1 and 2. Because those were where they were. So first is a pointer to the first node of the list. And then last is a pointer to the last node of the list. So first is 1, last is 2. Okay? And so that's where the memory was. Does that still make sense? Do you yell at me the second it stops making sense? Let's see here. I think that's most of what I wanted to say. So yeah, let me show you like the process. How would I use a linked list in practice? Let's make a slightly bigger list. Let's make 1, 2, 3 this time, and let's go through it. Let's iterate through it with a loop. So that's a thing we can do. Let's figure that out. So here's essentially the list I want to make in memory. Like first, it's very similar to what we just made. Like first is this. Boop, 1, 2, and then 2's next will be a 3 node, and that's the end of the list, and that'll be the last thing. That's what I want to make in memory right now. All right. So let's make that, and then we'll iterate through it. So I'll make a new file. I'll call that 123.cpp. And so I need 3 nodes, right, on the heap. A 3 node. 3's data is the number 3. And then 2's next is not null anymore, it's 3. 2's next is 3. And 3's next is the null pointer. That's the one that's going to be the end of the list now. 3's next is null. All right. So, and then first and last. First is still 1, but last is now 3. Boop. So that is That's the code that makes that list. Do you see it? All right. All right. Now the goal is let's iterate through this list that we've made, starting with first and going till wherever the end is. Okay. That's usually how you'll do it. So the trick is to go through pointers because everything is pointer based. So that is the secret. What you're going to do, the way that you would loop this is you'll say, all right, let me have my, what's your I variable? Kind of like, all right, node star, like where am I looking right now? It's always at a node through a pointer to it. So node star, like n or whatever, is started at first. That's the thing I'm looking at first. Go to that thing, right? Use it, go to like n's data, look at the data, and then advance that pointer to get to the next thing on the list. Like n is somewhere right now, like n is here. Boop. Once you're done, do that. And the way you do that is you say n equals n's next, because that'll now give you that address. Okay? That's how it'll look. So n equals n's own next. That'll now point to, it'll hold that address, which is now pointing to that node. Do you see it? That's how that'll work. So like then you'll use n's data again to get the 2 out. Then it'll be like n equals n arrow next to be like, all right, n now is whatever this address is, holding that address, which is the address of this node. So now n would point to here. And then finally, you'll play the game like, give me n's data, use it somehow, and then advance the pointer because I'm not sure if I'm done yet. N equals n arrow next. Well, n equals n arrow next is like, all right, get me n, set it to that address. Set it to the null address, something that doesn't exist. So then it's like pointing off into the ether. And that's when you know you're done. That's going to be the process. Okay, so let me show that to you. I'll do it first with a while loop. It kind of probably makes more sense with a while loop right now. So let's iterate. I want to start at the first node of the list, and so, oops, damn it. Why is that like that? Oh, that's what I wanted to do. Okay, let's iterate. So node star n equals the first node. Like n is going to be my window into the list right now, whatever I'm looking at right now. And I want to keep going while n is a valid node to be looking through. So while it's not equal to null, I want to keep going. And what do I want to do? Let's print out every element's value maybe. So we'll be like, okay, print the data part of n and then advance n to be the next node in the list. Okay, so I'll say, all right, I got a node I'm looking at. It's called n. Let's print n's data, whatever it is, and then we'll do like space to separate. And then I'm done with n now. I want to advance it. N equals, give me the next node on the list. The next node on the list is conveniently part of n. That's the address of it. Shove that into n now, and now it's pointing to the next thing. Okay, so that may be a little weird, but that will be how it works. And then we'll break the line. And this will print 1, 2, 3. That is not what I wanted to run. There we go. And so this is a very complicated program that prints 1, space 2, space 3, space new line. Are there any questions about what's happening? Do you see like how this diagram is playing out? Like this n equals n arrow next might feel weird to you, but can you kind of imagine what's happening there? Any questions at all about that? Because you didn't have to do it as a while loop. It could have been a for loop. Let me show that to you if we're ready for that knowledge. So like, all right, for loop version. And one day you will grow to like this way. I promise. Be like for, all right, node star m is the first thing instead of n. Keep going while m is not null. Then I have something to look through. And then what's my m plus plus? It's m equals m arrow next. That gets me the next thing. And now m is my window into the list, like cout m's data and a space and break the line after you're done. Same idea. Still probably very weird in our minds, but like it works. These are equivalent pieces of code. I've just used a different name, of course. Any questions about that? It's odd. It's odd, but it works. And we're going through addresses, so you got to be very, very, very confident about using pointers, because that's our life from now on. Are you ready for more knowledge? I'm going to switch gears to the ADT now. Are you ready for it? Okay. This is so fun for me. Okay, we've got the list ADT now. Let's talk about that. So remember the separation between data structure and ADT. So a data structure is like, I know what memory looks like. I can draw a picture. I know where all things are on the stack and the heap. I can make up addresses if I wanted to. I can draw boxes. ADT stands for abstract data type. It's something that's defined in terms of the way you interact with it. It's defined in terms of the operations you can do to it. So we're going to make a list ADT that kind of wraps around the kinds of things you would want to do to a linked list, but it does not have to be implemented with a linked list. It's just, if you're sane, you'll do that. But if you could totally do it with an array if you wanted to, or a vector. All right, so let's figure this out. Like, what kind of operations should a list ADT have? Like, what things are linked lists good at? What would it make sense to name them and all that kind of stuff? All right. So here are some ADT operations for lists. Here are some things that you might want to do. So, okay, you would want to like insert at the beginning of your list, insert at the end of the list. If you've tried your lab, that's the push front and push back of the C++ built-in lists. You should probably, the list should know its size, should know whether it's empty. The list should be able to maybe remove something, maybe from an arbitrary position, maybe from the start and end only. It's like your pop front, pop back. Maybe we should be able to search through the list for something. We'll figure this out. Like, I want to go through this list and find something, find a value, give me back maybe the address of where that node was so I can maybe change things or delete it, stuff like that. So that's kind of cool. Think about search right now. You want to search through a list because I'm going to ask you a question about that in a second. But yeah, that's kind of how that works. Let me show you kind of removal. Like, what would remove look like in a list? It's kind of fun to think about. Let me show you how easy it would be. It's like, let's say I had the list 1, 2, 3. And I didn't like the 2 node anymore. How would you get rid of it? You'd just be like, oh, give me that. Find me the node, first of all. Search for the node. Make sure it's there. And just, you have to tell its parent, or not parent, but the person before it to forget about it. It's like, that's not my node anymore. That's not my next thing. That's the next thing. Then you're safe to get rid of that on the heap, to delete it. That's pretty easy, relatively. Think about if you had to do that for like an array or a vector. Like, I don't like the 2 anymore. What would you have to do? You would have to, like, if there was anything after it, you'd have to move it before it. So again, it would be a linear time process in the worst case. Think of it as like if it was size 1,000,000 array. That's disgusting. And then you have 1, 3. And probably some extra space over there still that's not in use. That's kind of silly. So that's fun to think about. But yeah, it's kind of easier that way. But honestly, you could have done this, right? You could have implemented a list using vectors like this. Instead of this being your deletion, this could have been your deletion. You could have messed with things in a weird way. And ADT is just a list of operations that you would want to do. But an ADT is a list of operations you could want to do. And we're calling the ADT list. Like, what would I want to do with the idea, with the hope that we're going to use a linked list at the back end, but we don't have to, right? You can use an array as long as you follow all these rules. You play the game of being a linked list, or you play the game of being a list. You are a list if you do those things, okay? From the ADT's perspective, all right? So that's the idea. And now I have a question for you, all right? So let me draw a list for you. Let's say I've got, I don't know, just to make it concrete, here's my list. 1, 2, 3. Remember that's what a list looks like. 3, and you got pointers, to the front and end. Some people call them, instead of first and last, they call them like head and tail. You'll see those. But I'm purposefully not using them because I don't think last should be called tail. Once you get to advanced computer science, like this for sure can be called head, but the rest of it people call tail. So it gets a little complicated. Forget I said anything. So that's our list. Let's say we want to implement searching through a list. Like somebody gives me a value. Like I want to search for the number 42 or the number 1 or 2 or 3, something that maybe is in the list as well. If you choose to implement the list ADT in the normal way and you use a linked list as the underlying data structure, what should the worst case running time complexity of going and searching for something be? What must it be? All right. If we're going to use a list that looks like that, how must things play out? That's my question to you. Please remember to do attendance. I'll stop that when I forget. But please get together in groups, say hello, and this will be a little bike clicker class question. So please answer and convince your neighbors that you're right. Take a few minutes. Any questions about the question I can answer? Where n is the size of the list, by the way. We're always going to use that to mean the size of something. Let's see. Another minute to discuss.
I don't know how you do it. We also have to go to the expert.
All right, that is my timer. Are we ready? Get that answer in. Get our best guess. Let's see what we're thinking. Let's figure this out together. We are thinking C with the majority, and I do believe C is the right answer. Let us talk about it. So, for those of us, C is the right answer. Somebody who picks C, can you tell me why? Like, why did that seem right to you? Yeah.
You just have to iterate through every node to check for the number.
Yeah, there's no real concept of binary search for a linked list, is there? Does everybody see that? Because you can't get to the middle. You cannot immediately get to the middle of a linked list. You have to go through first. You have to go through first. Does everybody see that?
Yeah.
That's the bottleneck there. That's interesting. You cannot do binary search on a linked list unless you do something weird. You make a weird kind of linked list. There's a way, but it involves more pointers. Not this kind. This is called a singly linked list. We only have one pointer somewhere. Okay? So for this kind of list, it will be linear. And that's really good that we saw it, because you're kind of forced. Like, all right, if I'm looking for the number 2 or just anything in the middle of a size like 1 million linked list, you got to start your little end pointer at the start. At your first. You cannot go backwards. There's a way to go backwards in lists, but again, that's called a doubly linked list. You'll read about that in your book. We're not going to implement that in our labs. But it's good to know that other kinds of lists exist. Like we don't even have this ability to do that. There's a way to do it though. You can save a previous pointer rather than in addition to a next pointer, but we're just gonna do this way, one way only. If you're looking for something, you just gotta do that. You're forced to do, no matter how big your list was, boop, 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 just like you keep going through it in a linear fashion, in order, from left to right, from first to last, until the end. That's all you get. All right. And then, by the way, because it's worst case, by saying the word worst case, you should think about, all right, how long could it possibly take? You're looking for the 42. You're looking for something that's not there. You have to go through everything anyway. So it is going to be, that's another reason to think about why it's going to be linear time. But yeah, I mean, binary search is still impossible. It's worst case, even if there's something not there, it would be logarithmic time. But you got to go from left to right. All right. And that's great that we saw it. Any questions about this question? You all understand it? So you can't do any better than that with this kind of linked list. So that's fun to think about. There are ways to do some slight improvements though. So yeah, let's now talk about the list header. So I'm asking you to do a little bit with that in your lab. Let's go and talk about that. So there's a list type that's essentially the list ADT implemented by the C++ people that wraps around essentially a linked list. Let's figure out how that works. It is part of, this header list is part of a special piece of the C++ standard library. It's called the STL, which is short for Standard Template Library. Standard Template Library. And the word template is kind of important. We're going to learn how to make our own templated things later. But what that means is you say not just list, L, but you say a list, of ints. Just like vector of ints, vector of double. Like this part is the templated part. No one's probably ever told you that before. Now you know. So that's what makes it a template. Like you've made a blueprint for any kind of list ever. Like I can make one of ints, make one of doubles, make one of bools. That's what it means to be templated. But that's not important right now. So okay, let us look at the documentation pages. And I got a fun, silly example for us. So there's plenty of different pages you can look at. Just like search for C++ list. I like this website. But you can find it very quickly by going, I promise to stop that. You can find it very quickly by going, it's in the containers part of that website. You say list, and it's the list type. And then here's all the things you can do to a list. Get the begin, end, see if it's empty, get the size. A lot of things we talked about that a list ADT should have. You can add stuff quickly to the front or the end, push front, push back, get rid of stuff from the start and the end, pop front, pop back. And then you click on one, it gives you an example. It's like very similar, all right? And then it talks about iterating through. It's very cool. So let me show you a silly little program that has SpongeBob as the theme. So let us make a pre-made program. Let me copy in a pre-made program that adds these ingredients, because that's the Krabby Patty ingredients. It has to be in that exact order. I'm going to show you how to use some of the list stuff to do all that. Okay. So I need to copy that in. 241. This is lecture 9. To here. Cool. All right. So now I have the file. It's called krabbypatty.cpp. So here is a silly example of the list library. And I'm going to make a list of strings. So why not? It's templated. So I'm going to make a list of strings for the ingredients. And just like for vectors, like you say list something, semicolon, that's going to get you the default constructor. You can go click that, figure out what that's doing. It's going to make you an empty list. So constructor of a list, by default, it is going to be empty. Default constructor constructs an empty container with no elements. Yay. And you can see some examples. Empty list of ints. And then you can add stuff. There's other constructors. You can read about those. It's fun to think about. But yeah, ingredients is a list. It's initially empty. And then I can start saying push front and push back to get things in the right order. All right. So you can do push front to do things backwards. That's totally fine. Because like if you want, it's got to be bun then patty. You can push patty then bun as long as you add to the front. Right. That's kind of cool to think about. So here is pushing patty. So it's only a list of patty right now. And then if I add to the front bun, then it really is bun patty. See that? So it's kind of, you can go backwards. couldn't do that very easily with an array, right? And then you add the rest in some weird way. Like you can push them back at the end, and like that's just like how vectors work. So now the list has stuff in it. It's got a bunch of strings, and so deep down it really is a linked list, but you don't have to care about that too much. We're doing that, and let's see here. How do I want to say this? We'll eventually get to all that. So now the question is, I've got this list. How do I go through it? How do I print it out? How do I use this thing? Because it's an ADT. We're not like giving the people like pointers. We're not giving them pointers to nodes because maybe we didn't implement it with nodes. You could have done it with a weird arrays or something. That's the question now. How in the world am I going to print this list? How am I going to go through it? There's plenty of ways. One way to do it, there is you can make a vector out of your list in a weird way. There's like begin and end. There's one way to do it would be convert it to a vector with this kind of thing. There's a constructor on a vector that could take a list, surprisingly. And then you know how to do vector stuff, but that's kind of disgusting, right? That's going to be linear space complexity, right? Because it's going to copy it all over and make it the same amount of stuff. It's also going to be linear time complexity because you got to do the copying. So that's kind of not worth it. There's a way to stay with the list and go through it. And it has to do with these begins and ends. So that's, again, something that you're going to learn about more in your lab, but I should show you what all that is. So one way to go through, like however can we print our list, there's no .at, right? There's no indices even of a list, right? We don't have that. Let's go look. It's not there. We can't get in that way around a list. It's not accessible with indices or anything like that. We could convert it to a vector like I showed you, or we could use the concept of iterators. So that's where we're going right now. So this is again a kind of a wrapper around the idea of moving through something, which is cool. It works for many different kinds of types. So yeah, we know that if we had a linked list at our disposal, we had that access to the memory, we would use pointers. We would go around it with pointers. What do we use in a list when we have an ADT? Like what kind of thing do we get back? How do we move through the list in a way that is reasonable and doesn't have to like expose the user of the library to pointers to weird things that they don't understand? Iterators is the answer. Okay, so this is mostly the idea of an iterator. It's kind of a wrapper around me going through something, right? Iteration means I'm like traveling or something. So an iterator is kind of like, it's an object. You're getting back an object when you use iterators, and you get one. It's an object that is kind of wrapping around the idea of being a pointer as well. It's pretending to be a pointer. And so it doesn't have to be implemented using a pointer, but it's just an object that has the star operator like pointers overloaded. It has the plus plus operator like pointer arithmetic overloaded to like get to the next thing. It has equals and not equals to overloaded. Okay, so these exist for vastly different types, which is great. Like go look at vectors; they also have these iterators things, and they all work in the same way, which is very nice and powerful. But here's kind of how that works. You can say iterator section. You got begin and end. There's also other things that you should read about, but we'll talk about begin and end. What .begin does is it gives you back an iterator. The type is called iterator. It lives within the list as well. I'll show you what that means. But it kind of looks like this. My iterator, call it something, equals my list .begin. All right, and the full type is the type of the list : iterator. So like the type of the iterator to that particular list lives within the type of the list itself. So that'll look weird, but yeah. .begin gives you back an iterator to the beginning of the list. You think of it as a pointer if you want to. It gives you back an iterator to the beginning. Like if this is my list, 1, 2, 3. .begin gives me an iterator to here. So it's like looking at the one node in a sense. So you don't even need to think of it as a node. Just like think of it as an element. And then the .end. That one's a little weird. The .end of any iterator, for any kind of type, again, it gives you back an iterator, but it points to, or it looks at, one past the end. It's not the actual last element. It's one past the last element. All right? So really, you think of .end as this, past the 3. .end is a place you would never want to get. So that's kind of when your loop stops, if you want to think of it that way. .end is one past the end. It's somewhere that I don't want to be. All right? And so the reason, and then kind of here's some weird code that I will explain in detail in a second. But it looks like this. You start the iterator at begin. You could use star IT to get the thing it's looking at right now, and you can do IT++ to get to the next thing. So like keep going as long as it's not the end, because that's like too far. That's kind of how that looks. All right. Whee! So that's something to keep in our minds. And the reason iterators were built this way, it's like a class that wraps around these kinds of operators, is it's kind of trying to be pointers and arrays. It's trying to make everything look like pointers and arrays for vastly different kinds of things, just like lists. So here's the reason we've chosen to overload exactly those operators, because here's one way that you could iterate through an array in a weird way. So here's an array, 3, 4, 5. Let's think about it in terms of addresses. This is just like historical facts right now. So the array itself, let's say that this starts at address 100, this is 104, 108 in that case. R, if you just say R, that's just 100. It's a pointer to its first element. That's what an array is. That's how you represent arrays. You are allowed to, because that's all R is, it's just a pointer to its start, you can make an int star. You can set that to R. It's like P equals R. It's holding the same address. It's the 100. And so P also points to 100. And you know that you could like use a pointer by dereferencing it. You could say star P, get me to the 3. That's why that exists. And then you could also advance your pointer if you really wanted to. You could play this game. You could use the indices like P of 1. That works. But really what it's doing is it's doing like some weird pointer arithmetic and doing some dereferencing for you. So you could have done it this way. You could have been like, you know what? P++. P equals P plus 1. That will change this P to not point to address 101. It's going because it knows it's a pointer to an int. It'll point to one int address later, which is 104, which is now going here. And so you could get through an array by saying like star P starts at the beginning, star P to get the thing, P++ to move it. Does that make sense? That's what you could do. And that's kind of what iterators wrap around. Okay. So with that in mind, now we can go through the Krabby Patty ingredients with your list. And then this is what it looks like. You're going to say my list dot begin. I'm getting back an iterator to the start of it. For us, it's a list of strings. A list of strings, and you say colon colon iterator. The type of the iterator lives within the type of the list, which is odd, but it does. All right, that's the full type of your iterator. If you have a list of strings, you say dot begin, you're getting back a list of strings colon colon iterator. If you have a list of ints and you say that list dot begin, you're getting back a list of int colon colon iterator. The type depends on the kind of list, which is interesting. So that is that, and here is what we've been working towards. Here's how you can go through the list using iterators. Okay, here's how it works, and let me. I don't know. I don't need to comment it out. We'll do it in order, right? So here, Patty. All these things are ways to print the same stuff, so it's not really that big of a deal. Here I am in a bunch of different ways going. It's printing them out in order. We did it the vector way first, and then I'm doing it with the iterator way, and it's still working. All right. Here's how it's working. It's like it's going this way. So it's like 4. I've got an iterator that starts at the beginning of my list. It's a list of strings. So it's a list of string colon colon iterator. I'll call it IT. That's the name of my iterator. All right. That's how it starts. Let me do it. Let me zoom out a little bit so you can see that. So there it is. And then we would like to hit the body. We want to keep going as long as IT is not equal to the end, because that end is really 1 past the end. .end gives you an iterator to 1 past the end of the list, which is a place you don't want to be. So keep going as long as that's not true. There's no concept of like less than or greater than. There's a concept of equal to and not equal to, though. So that's that. And now IT, this iterator type, has the star dereference operator overloaded. So somehow it knows, if you say star IT, it knows to get to the string, this is a list of strings, it knows to get to the string you're looking at right there. Like it's looking at something, give me that string by saying star IT. It's the string at the current node, if you want to think about it that way, because it's a list. But this will still work for vectors. If you try it this way, it'll be a vector of string iterator, blah, blah, blah. Yeah, that's how that works. And then you say IT++ or plus IT to get to the next thing. And you just keep on doing that as long as it's not at the end. So that's what iterators give you. They give you a way to go through something in a controlled way without having to deal with actual pointers. It's like wrapping around the idea of being a pointer and moving through something. Does that make enough sense? Any questions about that? Like it's just weird syntax, but you'll get used to it. But that's what iterators do. And the C++ people have been very nice to us. They've made iterators. They've made begin and end for vectors, for lists, for all the other things I'm asking you to discover in your lab. The iterators still work pretty much the exact same. So that's really nice across vastly different types. I love that. So there's that. Yeah. And then also, if you've seen this before, this is a fun thing. It's disgusting, right? It's disgusting to say this. List a string, : iterator. Let's see, do I want to do it that way? No, eventually. It's a lot of typing, right? This is a very long loop. If only I didn't have to say that. There's a better way. There's a fast, if you want to go through your list in order, have we seen this? I guess I've used it once, at least. But this kind of syntax goes through, like you use this with vectors, right? For everything called elem in some sort of container, like a vector, or a list this time. This is called a range-based for loop. Have we seen this before? We remember it at least? That's how you do it. You say the type of thing, you give it some name, and you say colon. Colon means in. It's like for every string that I'll call elem, in my list called my list, go through it. It's going to go through it in order from left to right. And this elem thing, whatever you put here, it could have been x. This elem thing is going to be set to the current element it's looking at. All right, so that's called a range-based for loop, and it does secretly iterator stuff. Excuse me. I guess I'm allergic to the shortcuts, but this is what it looks like. All right, that's what it looks like. And this code, if you do it this way, you get no difference. Like it just printed them out again. You could have set it this way. For every, it doesn't have to be const string, but I'm not gonna mess with it. So like you can take it by a constant reference. I could have said string elem, but I'm doing it fancy. For every elem that is a const string reference, because I want to go through the ingredients that way. In the ingredients list, elem gets set to the next thing, and I want to use it. And I want to use it. This code, surprisingly, this code turns into this code. The compiler does it for you. So secretly, if iterators exist, this code becomes this. Does that make any sense at all? That's very odd, but that's why this works. You've done it for vectors. It's been using, is why it doesn't work for arrays. This code secretly turns into this code, and it uses begin and end on ingredients. And it gets back each string by doing it. It does the star on the iterator that it's looking at. Like all this code gets translated into this code, which is very nice. Okay, so yeah, if you want to go from left to right, you didn't have to type all this out. You could have used this, but the reason it works is because of iterators. It's using iterators deep down. You need to learn that first. Okay, any questions about that? So we've seen that syntax before, right? Works for vectors, which means vectors have iterators. You could have done this on a vector, which is great. One last thing, just to make it nice. This is C++. When I say C++ 11, that's the 2011 version of C++, which is pretty old by now. Came out a long time ago, but it's useful. People love it. There's one more thing that maybe you have not seen yet. It's called auto. Have any of us heard of that? I forget if the CSCI 40 textbook I use even talks about this, but it's a way. Auto is a way for C++ to infer things. It figures out what type you meant. So instead of saying, this is a silly example because it's more typing, but instead of saying int x equals 42, you could have said auto x equals 42. It's one more character, but it's odd. And what would happen is it'd be like, oh yes, you're assigning x to an int. I know the type of 42 is an int, so the type of x is in it. Like it figures it out automatically. That's what that does. So that will save you some typing if you want to use iterators, I think. It requires declaration and initialization, because if you just said AutoX semicolon, of course it has no clue what you're talking about, right? You got to give it something, and it's able to, because like C++ is checking types all day long, right? It's trying to make sure things match. So it knows the type of 42 is an int, and it's like, okay, yeah, if you wanted me to infer the type, you gave me an int, x is an int. It gets it. So that's quite nice. So there's a middle of the road approach here now. It's like instead of doing this and going all the way here, you could have said auto it equals ingredients.begin. Does that make sense? Like it would have figured out this long type for you. That's the last one. So yeah, C++ can infer that type based on what you get back from ingredients.begin, like because it knows the return type of all that, like .begin, this one. It gives you back an iterator to the type of your list. So it's like, oh yeah, that's what it should have been. It should have been a list of string : iterator. That's the type. Cool. And then you can do that. So that makes it more like shorter and better, I would say. And so you still get the same thing, but now it figures out the type for you. So when you have long types and it's clear what it should be anyway, you're good to use auto. So yeah, now you know. Does that make enough sense? Any questions about any of those things? So just iterators. It's a way, it's a wrapper around the idea of like a pointer. It's a way to look at something and go through a type of thing. So go through a sequence of things like a list or a vector or anything that you could want to make. Any kind of container. That's what C++ calls them. They're containers. Right? Yeah. I think that's most of what I wanted to say. Are we ready to talk about how to make our own version of the list ADT? So just shout out if you have any questions about anything. But that's the last piece of today. Not too many slides left. So let's learn now. All right. We know what a linked list is. We know how to make the struct node stuff. We know what a list ADT should have. These things. How do we implement them? If we choose to implement using a linked list as our underlying data structure, how do I make all these things happen? So let's figure it out. Okay. So I'm going to give all this to you in pseudocode as well as diagrams. So of course, like this will eventually be turning into a lab for you, of course. There's that. Let's figure this out. All right. So, okay, we want to make a list. It's called a list. We'll use capital L. We'll call it a list. All right. So how do we hold on to our list is now the main question. We're using linked list deep down. So the way that we represent a linked list, the way that I've been drawing it, where is it? Is we've got pointers to at least the first and the last nodes in our list. That's pretty much what we're going to use to represent a list. Like, how do we hold on to a list? We're going to hold on to the start of it and the end of it. The first node and the last node. Sometimes the first is the last, right? Because it's the very first element you put in there. That's fine. But like, that's what we're going to do. All right, that's the way we're going to choose to do it. So our data inside of every list object that we could make, you say, I don't know, list L. What does L look like in memory? It's going to hold on to a first and a last. All right, that's what that will look like. So we're going to store those pointers, and that's all we need inside of our list objects. The rest we can get through by following next pointers. All right, so let's say we did this, and we did like L dot pushback. I don't know, 43, and then we did L dot push front 42. This will make the list 42 then 43, won't it? That's cool. So then living on the heap, the memory would look something like this. You made the 42, we made the 43 first. That was the only thing. But eventually you also made the 42, did that, and now this is first, and this is last. So that's what the memory is gonna look like. That's what we're gonna make happen eventually. Okay. Some people call first head. Some people call last tail, like I said. I'd rather you think of tail in a different way, so that I'm not going to go there. But head, people agree. Like, that's the very first thing. It's the head of like the centipede or whatever. Yeah, that's what we're going to store in every list object. That's all that we need. Okay, that's all that we need. Where's the first thing in the list? Where's the last thing in the list? Everything else we can get from there. We can follow enough next pointers to get to where we need to go. Okay. And again, we didn't have to use linked lists. We could be weird, and we could use some long, weird string that we would parse each time we deal with our list. But like, you could have used an array to implement a list ADT. Like, I don't know, instead of first and last, you could have held things as an array. Like, every time you make a list L, it makes a secret array inside, and somehow you're like resizing it. Maybe it's on the heap. I don't know. You could turn it into that. Those are 42, 43 in that order. But nodes are better. I think the kinds of operations we want to do just are better suited to nodes and a linked list. Okay, so yeah, let's figure this out now. We know what lives inside of all of our lists now. Every time you say list L, semicolon, we know that the data inside is first and last. That's the only member variables we need. First and last. Whee. Dun, dun, dun. By default, the default constructor is going to, like, these are pointers, right? It's going to set these to garbage. And so we should start our list out empty somehow, like to mark the fact that it has nothing in it right now. And that's my next and final question for the day would be like, what in the world? What do we need to do here? Like, if I say list L, this won't be the longest discussion, but like if I say list L, like what should we do to say, how should we mark the fact that the list is empty? If we have first and last, what what are our options, I guess. And so I'd like you guys to please discuss that for a minute or two. It shouldn't take a whole lot of time. There's not too many different options, but like, what's the right one? So please take a couple minutes to write down, please, on the nice page as a group. What do you think we should do here? How can we indicate that the list is empty for us later, right? Because we're implementing all this stuff. How can we mark it? Questions about the question? There are options. See if you can figure it out. There's a few ways. First and last are pointers to nodes. That's the kind of things that you can put in there. They're holding addresses of nodes. All right, I think that's enough time. Are there any questions that came up? Are you ready to discuss? Let's see. Yeah, I was saying they'd probably be the same thing somehow, but a lot of us have decided that null is a good idea, which is good. I think that's one easy way to mark the fact that the list is empty, just by saying, oh yeah, if first, they have to both be null, right? If first and last are null, then there is nothing in the list. They're pointing to nowhere. Does that make sense? That's a good one. There is another competing school of thought. I forget if your book talks about it. Because first and last are pointers to nodes, like you're either going to put a node or not put a node. Yeah, you can't keep it garbage because that's bad. But you could put a node there. You could put one node that's the first thing and the last thing at the start, at least. You could put some node that's like marks that it's empty somehow. There could be one like default node, like it's a dummy node they call it, that could just mark the fact that you have a list but nothing's in it yet. And everything that's real happens after that one. That's a competing school of thought. You could get away with doing that. There's a way to make everything work in that way. But yeah, it's easier to use null, I would say, and just check against null all the time. Okay, so yeah, let's talk about like a decent algorithm now. So let's say we would like to do an insertion algorithm. Let's say it's easiest for a list to insert at the start or the end, so like this kind of push front or push back kind of operations. Let's have those in our ADT. Those are the ones we want. And let's talk about push front right now. There's plenty. We'll talk about push back next time. It'll be similar yet slightly different. But let's do push front and talk about the algorithm. Okay, let's say I've got a list and I push something to it. Okay. So let's say I've got my list and I say it's called L, and I say L dot push front 42. It's a great exercise to think about how this changes if you were to do push back before next time. Let's see here. There are two options, honestly, so I need to draw both, and I'll just explain it later. But either the list was initially empty, and this is the first node you added, like something changes. So I need to show that to you. So let's say maybe the list was empty like we just had before, like it's supposed to be an L. Curly L. Maybe this was your list. That looks like an upside down gamma, too much to me. I am sorry. There. Either your list was empty or it had stuff in it, at least one thing. So let me draw both options because it's gonna work slightly differently. You have to check against these options. Let's say it's got some stuff. One, two, it could have had just one thing. So either your list looks like something like that, it's completely empty, or it has at least one thing in it. The algorithm's going to change slightly depending. So, okay, I'll draw in green now the new stuff. Like, what do you got to do? Say that one of the, like this is our list or this is our list. What happens now? If you're pushing front something. Okay. Well, always what's going to happen in either case is you're making a new node, right? You're making a new node on the heap, and its data is going to be that thing you're trying to add. So its data value is going to be the 42. 42. Either that or that, right? You're still making it in either case, yes? That's totally what's going to happen. And then what you want to do, let's do maybe the general case first, because like that's what's going to usually happen. Then you want to take that node and make it the start of the list, right? You want to make it the front of the list, which means it's next. Well, eventually we're going to say this, right? First equals that brand new node, but we can't do that yet because we need to remember the old first, because that's going to be our own next, right? And that's now the second thing. The old first is now the second thing. Does that make sense? Yeah. So we need to remember that address, and we have it right now in first, so we better use that before we get rid of it, or we chop that pointer away. So we want to bring that node into the front of the list by changing our new node's next pointer to be the old first element. So like this one, we have its address through first right now. Use that to our advantage to say 42's next is the old first, because now that makes it the second thing, right? And then you set the first pointer of the list to be that new node. Now it's okay to chop that off and make it point to here, because we can still get to this node through our new first now. It's all happy and everybody's great. And this process still works. All these things still work for the empty list. This will still be fine, and it'll do it right almost. So this will say the first's next, right? The next thing is the old first element. The old first was null for an empty list. That's exactly what we want right now, isn't it? The next of 42 is nothing. That's great. It's the old first. Bring it there. Still works. And then the first of the list is now that new node. So that still checks out. Both of those, it works for either kind, right? But what have I forgotten to do with the empty list? Last is not set. So last doesn't have to change if there was something already. It's still that last thing I'm adding to the front. But if there was nothing, right? There was nothing at all before, there is now something at the end, all right? So the list happened to have been empty. When you pushed, you'd check against last and be like, is it null or not? That would be your code, right? If last is null, that means the list used to be empty now, but now it's not. So then you must change first and last, right? First is changed to that new node, and then also last is also the new node, right? Last is the same. They're still matching each other because the first thing is the last thing for a size 1 list. Yeah. And so that's one extra final step if you need to do that. That's a possibility. Any questions about that? Does this algorithm make enough sense? So highly encourage you to draw these pictures. Like think about what would happen for push back. How would it change? Slightly different. But the last piece of the puzzle is let's do some running time analysis. Maybe do I want to do it like that, or do I want to do that next time? Let's see. Just briefly, I can add things in later, but like, what is the running time analysis of this? If we want to think about it that way, to make a new node on the heap, that's constant. To put it at the front by changing some pointers around, it's just like a couple lines, right? Constant, constant again. If the list happened to have been, let's see, how do I want to do that? Empty, it's still like an if statement. So like, think about how that would change. I think I'm going to talk about it in detail next time. It's probably better for you to think about it yourself. So like, try to do that analysis. Like how long does it take? How long does it take? Think about it like that. And I think that's where I want to leave us in terms of content. We'll get back to, and we'll talk about pushback. We'll do an actual in-depth analysis, but we'll do all that next time, I think. Yeah, are there any questions about anything we talked about? So linked lists, the ADT for lists, how we might start implementing things. You start thinking about how you might do the rest. And then we've also got the C++ list type and their iterators, because you're going to need those one day anyway. Are we happy with all that stuff? All right. So I think if we're good, that's what I wanted to say for the day. I'll give you a new lab, but that'll be next time. And so the rest of the time is all yours to like work and study and ask questions.